continue our discussion on the two-body problem, in which we will consider two particles which are interacting through a potential energy distribution which depends only on the distance between the two particles. This is known as the central potential problem, and in this, for such a case, we have a major simplification. The two-body problem can be reduced to two one-body problems, one describing the uniform translational motion of the center of mass and the other describing the internal motion of the two-body system. So, we had first considered the hydrogen atom problem or hydrogen-like atom problem, in which there were two particles and the potential energy distribution in the CGS system of units was equal to minus ZE square by R, where ZE represents the charge of the electron. So, this is the hydrogen-like atom problem, hydrogen-like atom problem. Now, we solved the Schrodinger equation and we had found that the energy levels, the bound state corresponds to E equal to E n minus Z square C square alpha square mu by 2 n square, where c is the speed of light in free space and the value of c in CGS units is 3 into 10 to the power of 10 centimeter per second. Alpha is the fine structure constant, which is about 137, and mu is the reduced mass, that is ME Mn. Mn is the mass of the nucleus divided by Me plus Mn, and n was the total quantum number which can take the values 1, 2, 3, etc. Now, we said that usually in spectroscopy we write the energy levels in wave number units, and we divide the term value for each state is defined as E by hc, where h is the Planck's constant and c is the speed of light. So, you will have E n by hc, and this will be equal to minus z square by n square. One of the c's will cancel out. So, you will have mu c alpha square by h, mu c alpha square by 2h. This quantity is known as the Rydberg constant. So, we write this as equal to minus z square by n square into r, where r is known as the Rydberg constant after the physicist Rydberg, and its dimensions in CGS units is centimeter to the power of minus 1. So, the energy levels are usually in spectroscopy, the energy is measured in wave number units, which is centimeter to the power of minus 1. And as I had mentioned, that the value of the Rydberg constant, as I had mentioned, that was equal to 2 mu c alpha square by 2h, and mu is the reduced mass. And since for different one electron atoms, the mass of the nucleus is slightly different, so the Rydberg constant is also slightly different. In fact, we had mentioned that for the hydrogen atom, in which the nucleus consists of just the proton, in the case of deuterium atom, the nucleus consists of deuteron, 1 neutron and 1 proton. For the helium plus atom, the nucleus consists of 2 neutrons and 2 protons, and in each case it is a single electron atom. Here Z is equal to 1, this is also Z is equal to 1, this is Z is equal to 2, and this is 3 protons in the nucleus, Z is equal to 3. So, because of the fact that in each case the mass of the nucleus is slightly is different, therefore, it leads to slightly different values of the Rydberg constant. And indeed, from the fact that the Rydberg constant is slightly different for deuterium, it led to careful measurement of spectral lines which were slightly shifted from that of the hydrogen atom, and which eventually led to the discovery of deuterium or heavy water by Urey in the year 1932. Now, this therefore completes the energy level structure. One thing that I missed out in my previous lecture was to give the detailed expression for the wave function. As we know that rho was defined, the dimensionless parameter was defined as gamma r, and gamma square was equal to minus 8 mu E by h cross square. This was the definition of the gamma square. Now, E takes negative values, as I have just now shown that that the expression for E sub n is this, and if we now substitute it here, then you will get plus 4 z square c square alpha square mu square by n square h cross square. So, therefore, gamma is equal to 2 z c alpha mu divided by n h cross. Now, the quantity c alpha mu by h cross, this is equal to alpha is equal to E square by h cross c. So, this becomes c E square mu by h cross square c, and so therefore, this becomes h cross c. So, the c cancels out, and this is known as the inverse of the Bohr radius. So, the Bohr radius is defined as h cross square in the CGS system of units m e square, and in the MKS units, this is in the CGS units, in the MKS units it will be mu q square by 4 pi epsilon naught. So, this will be equal to h cross square by mu q square, and on the numerator 4 pi epsilon naught. The value of the Bohr radius, as you must be knowing, is about half of an angstrom. Angstrom is 10 to the power of minus 8 centimeters, or this is equal to about half 0.5 into 10 to the power of minus 10 meter. So, therefore, we have shown that C alpha mu by h cross is 1 over a 0. So, therefore, we get gamma is equal to 2 z by n a 0. This it is better to remember this particular expression for the parameter gamma. Now, I will discuss that we had the radial in my last lecture. We had derived the expression for the radial part of the lecture as n normalization constant rho to the power of L e to the power of minus rho by 2, and it is a very easy formula to remember, F11 L plus 1 minus n 2 L plus 2 into rho. This is the confluent hypergeometric function, and as an example we will calculate the R31 of R. So, if you want, just as an example, so n is equal to 3 and L is equal to 1. So, this expression becomes F11 L plus 1, that is 2 minus 3 is minus 1, 2 L plus 2, that is 2 plus 2 becomes 4 times rho, comma rho. So, as you know, this is the value of A and this is the value of C. So, the confluent hypergeometric equation, as you would remember, is 1 plus A by C, that is A is minus 1 by 4 into 1 factorial, which is 1 times rho, plus A into A plus 1, but A plus 1 is 0. So, this and all other terms will be 0. So, therefore, we will have this as n, L is 1. So, this is just rho times 1 minus 1 by 4 rho e to the power of minus rho by 2. Now, let me normalize this wave function. So, we will have the normalization condition is integral 0 to infinity R31 of R whole square R square dr. So, rho is equal to gamma r. So, r is equal to rho by gamma, and therefore, r square will be rho square by gamma square. This will be d rho by gamma. So, there will be so normalization condition is 1 is equal to so much. So, this will be rho cubed divided by gamma cubed. So, if you square this, so you will get this is equal to n square by gamma cubed integral from 0 to infinity square of this rho square, and if I square this 1 minus rho by 2 plus 1 over 16 rho square e to the power of minus rho times rho square d rho, I have taken the gamma cube outside. So, therefore, gamma cubed, if I take gamma cubed in this side, so n square 0 to infinity. So, this is the first term is rho to the power of 4, minus half rho to the power of 5 plus 1 over 16 rho to the power of 6 e to the power of minus rho d rho. The integrals are very straightforward. They can be written in terms of gamma functions. So, this is equal to n square brackets gamma of 5, which is 4 factorial, minus half of 5 factorial plus 1 over 16 of 7 factorial, and that is it. So, if you do the algebra, so this is 24, and this is 24 into 5 divided by 2, that is minus 60 plus 24, I am sorry, this is 6 factorial, I am sorry, 24 into 5 into 6 divided by 16. So, this is 4, 6, so 45. So, this is just 9. So, this is 9 n square, 9 n square. So, therefore, we will have the normalization condition. Normalization condition will lead to 9 n square is equal to gamma to the power of 3. So, this leads us n is equal to gamma raised to the power of 3 by 2 divided by 3. Now, there is one more thing that I would like to mention, that R31 of R, as I had written, was n is gamma raised to the power of 3 by 2 divided by 3, this is this factor, multiplied by rho. Now, rho is usually written as is equal to gamma r, and as we had derived, gamma value was equal to 2z by n a0 into r. So, in this particular case, this will be 2, n is 3, and z by a0 into r is denoted by xi. So, this will be multiplied by rho into 1 minus 4 by rho by 4 e to the power of minus rho by 2. So, the rho is 2 by 3 xi. So, 2 by 9 gamma raised to the power of 3 by 2 into xi into 1 minus rho is equal to 2 by 3. So, xi by 6 and rho by 2 will be xi to the power of. This is usually the radial part of the wave function is written, and then you substitute for gamma equal to gamma will be 2z by n a0. If you finally substitute that, you will get with simple substitution 8 upon 27. I leave it as an exercise, z by a0 raised to the power of 3 by 2 xi minus xi square by 6 into e to the power of minus xi by 3, where xi is equal to z r by a0, and a0 is the Bohr radius. So, this is the rigorously correct normalized wave function, and it is this form, it is in terms of the variable xi that most of the wave functions are written. What I would like to conclude this part of the lecture is by saying that I leave as an exercise for you to calculate from first principles R10 of R, R21 of R, and R30 of R, R3 of 1 of R I have already calculated, R32 of R, and then n is equal to 4, R41 of R, etc. These are fairly straightforward to calculate, and once you get the hang of calculating this, you will find that the use of the confluent hypergeometric function is extremely easy in the calculation of the normalized wave functions. So, this concludes the hydrogen atom or hydrogen like atom problem, and we will continue on the two body problem, namely that of the Deutron problem. In our last lecture, we had started on the Deutron problem. In the Deutron problem, we have one proton and one neutron. which are held together by a potential energy distribution, and we had assumed a very simple model, and we had assumed that the potential energy was that this is V of r, this is V of r, and the potential energy was infinite at r is equal to B, and then it was very deep and equal to minus V 0, and then it was 0. So, this coordinate is r. So, this is r is equal to B, and this is the point r is equal to A plus B. So, therefore, we had assumed that the interaction between the neutron and the proton can be described by a spherically symmetric potential, and it is given by V of r is equal to infinity for r less than B is equal to minus V 0 for r less than A plus B and is equal to 0 for r greater than A plus B. Now, therefore, at r equal to B, the wave function must vanish, and we wrote down the radial part of the Schrodinger equation and solved it for L equal to 0. And we found that in the region B less than r less than A plus B, the solution of the radial part of the Schrodinger equation was sine of k into r minus B, where k square is equal to 2 mu by h cross square E minus V, but V is equal to V 0. So, it is V 0 plus E, but we are considering the bound state problems. So, the energy, discrete energy will lie somewhere here. So, the energy itself will be negative. So, therefore, we write this as 2 mu by h cross square V 0 minus modulus of E. And when we find out modulus of E, we will remember that E itself is a negative quantity. Then for r greater than A plus B, the solutions are exponentially decaying. So, u of r we said that will be equal to B into e to the power of minus kappa r, and kappa square was equal to 2 mu E by h cross square with a minus sign. So, this is equal to 2 mu by h cross square mod of E. Okay. Then we made u of r and its derivative continuous at r is equal to A plus B, and similar to the one dimensional equation, we arrived at the following transcendental equation: xi cot xi is equal to eta, which was equal to kappa A, where xi was equal to Ka, and so therefore, xi square will be equal to k square A square. So, 2 mu by h cross square V 0 minus mod of E A square, and eta square was equal to kappa square A square. So, this will be equal to 2 mu by h cross square. These are all dimensionless quantities. So, if you add them up, xi square plus eta square. So, this term will cancel out with this term. So, we will get 2 mu V 0 A square by h cross square. So, this is a dimensionless number alpha square. So, my eta is equal to under root of alpha square minus xi square. So, this equation becomes the following transcendental equation: xi quad xi is equal to under root of alpha square minus xi square. For a given system, that is for a given value of the reduced mass, the potential energy depth, the range of the potential, and of course, Planck's constant is a constant, the value of alpha is known. So, for a known value of alpha, we have to solve the transcendental equation and obtain the value of xi. Once we obtain the value of xi, we can calculate the value of E. Okay. For example, if I divide xi square by alpha square, if I divide xi square by alpha square, so please see this, you will have 2 mu by h cross square v 0 minus e a square divided by 2 mu v 0 a square by h cross. So, this will be v 0 minus mod e divided by v 0. So, this will be 1 minus mod e by v 0. Okay. Now, let me consider a simple example, simple profile, and calculate the value of alpha. And the value of alpha is under root of 2 mu v 0 a square by h cross square. Let me do this on the next page. So, you will have alpha is equal to under root of 2 mu v 0 a square by h cross square. We consider the neutron proton problem, and therefore, mu is equal to mass of the neutron, mass of the proton divided by mass of the neutron plus mass of the proton. If you substitute the values of this, then you will get about 0.8369 into 10 to the power of minus 27 kg in MK system of units. I assume V 0, the depth of the potential, is equal to 40 MeV. So, this is equal to 40 into 10 to the power of 6 electron volts multiplied by 1.602 into 10 to the power of minus 19. This is the joules. And we assume A is equal to about 1.9 Fermis. This is a typical value, 10 to the power of minus 15 meters. This is the range of the potential. So, let me substitute it here. So, you will get alpha is equal to 2 into 0.8369 into 10 to the power of minus 27. This is the reduced mass of the neutron and the proton. V 0 value is 40 into 10 to the power of 6, 40 MeV into 1.602 into 10 to the power of minus 19 multiplied by, in the denominator, a square, 1.9 into 10 to the power of minus 15 square, the whole thing under the root, divided by h cross square, and the h cross square is 1.055 into 10 to the power of minus 34 whole square. If you do this very simple calculation, then this comes out to be approximately 1.865. Alpha is 1.865. So, for the neutron proton problem, this is an approximate calculation. So, alpha is about 1.865. So, we go back to this transcendental equation. So, we have calculated the value of alpha. So, the transcendental equation becomes minus xi cot xi is equal to under root of 1.865 whole square minus xi square. So, I plot as we had done at xi equal to 0, this goes to infinity, this goes to 0. So, the product tends to a finite number, and the first 0 occurs at pi by 2. Pi by 2 is about 1.57. So, it is something like this, and it becomes infinity at pi, cot xi becomes infinity as we had discussed earlier, and so on. So, this is 3 pi by 2, and then it goes in again to infinity at 2 pi. Now, this is pi, this is 3. So, the radius is 1.865. So, we have to draw, so it will be on the right side of this. So, if I plot that arc of a circle, so it will be somewhere between 1.75 and 5. So, it will be something like this. This radius is alpha, and in this case alpha is 1.865. So, this is the point. So, this is the horizontal axis is xi. So, this is eta is equal to so much. So, this is my eta. So, at this value of xi will be between 1.57 and 3.1. If you do this, then it will come out to be, xi will come out to be 1.81. Remember, when you do the numerical calculation, this xi is measured in radians. So, 1.81 times cotangent of 1.81, if you calculate that, then this becomes about plus 0.44, and this becomes, if you 1.865 whole square minus 1.81 whole square comes out to be about 0.449 or 45, something like that. They are approximately equal. So, for this value of xi, for this value, this is the method for solving the transcendental equation. For this value of xi, the left hand side becomes equal to right hand side, and so therefore, that is the root of the problem, that is the eigenvalue, that is the eigenvalue. So, therefore, you will have from this equation 1 minus mod E by V 0 is xi square by alpha square. So, let me write it down. So, let me write it down here, that 1 minus mod E by V 0, we had derived this earlier, is equal to xi square by alpha square. Xi square we found, that is about 1.81 square, and this is 1.865 square. So, if you divide this, then you will find that this is about 0.947, and you take E by V 0 is equal to 1 minus 0.947 and into 40 MeV, and this comes out to be about 2.3 MeV about. So, the binding energy of the deuteron according to our simple analysis, simple model, comes out to be 2.3 MeV, and the actual experimental value, is minus 2.25, I think. There is one thing that I would like you to understand, at least for the L equal to 0 case, which we have been considering, there is only one bound state. There is one bound state. So, therefore, you will have here only one bound state, which is deep inside it. This is the bound state. The wave function goes to 0 here, and it is exponentially decaying here. So, this is the ground state wave function corresponding to the hydrogen, corresponding to the deuteron problem. So, we have solved the fundamental problem in nuclear physics. What is this simplest atom in atomic physics? That is the hydrogen atom or hydrogen-like atom, which consists of only one electron. So, we have solved that hydrogen atom problem, and the fundamental problem in nuclear physics is the deuteron problem. The hydrogen nucleus consists of just one proton, and the deuterium nucleus consists of one proton and one neutron. So, we have found that if we assume a potential energy, hardcore potential energy distribution like this, and if we assume V0 to be about 40 MeV and the range of the nuclear force is about 2 Fermi, then one gets a binding energy of the order of the value which is observed by the experiment. So, we have solved also the deuteron problem. We next consider, this was the second example. First example was the hydrogen-like atom problem. This is the second example, and now we will consider the third example, third most fundamental problem in molecular spectroscopy. The simplest molecule is a diatomic molecule like hydrogen chloride, which consists of one hydrogen atom and one chlorine atom. Okay. These molecules in the first approximation can be assumed to be something like a dumbbell. They can undergo vibrations which lead to vibrational energy of the diatomic molecule, and they can rotate also with their center of mass will move in a straight line in a chamber, but you can have rotational motion and vibrational motion. The rotational motion gives rise to what is known as the rotational spectra, and the vibrational motion gives rise to the vibrational spectra. And by carefully measuring the spectral lines, one can find out the interatomic distance between the molecules, what is the force constant describing these small vibrations. So, our third example that we will be considering is the vibration rotation spectra of diatomic. Diatomic means the molecule have two atoms. Let the mass of the two atoms be m1 and m2, and this is the distance r, and we assume a Hooke's law type of force, so that there is an equilibrium distance Re, and if you displace it in any direction, then there is a restoring force which tries to bring it back to this equilibrium thing. So, such a Hooke's law type of force, in which the force is proportional to the displacement from the equilibrium separation, is described like in a harmonic oscillator, is described by a potential energy distribution which is half k r minus Re whole square. If the distance between the two molecules is Re, then this is 0. If you displace it one way or the other, then it will lead to a restoring force, and the corresponding potential energy distribution is given by this. Since the potential energy distribution is assumed to depend only on the distance between the two particles, once again the two particle problem can be reduced to a one particle problem, and the radial part of the Schrodinger equation, the radial part of the Schrodinger equation can be written as, many people put two dots over O. Schrodinger, this is Schrodinger was an Austrian physicist, and so you will have d2u by dr square plus 2 mu by h cross square E minus L into L plus 1 h cross square by 2 mu r square minus half, this is the potential energy term, minus Re whole square. This is the Schrodinger equation describing two atoms which are held together by a Hooke's law type of force, such that the potential energy is k times half k r minus. This k is known as the force constant. Force constant. Now, let me look at this term. So, what we will do is, in order to solve this equation, we will introduce a variable rho which is defined to be equal to r minus Re. This is not the same rho as we had discussed in the hydrogen atom problem. This has the dimensions of length. So, this term becomes E minus, in spectroscopy, the angular momentum quantum number is written as J, it is just a convention. So, as we all know, L is equal to 0, 1, 2, etc. So, we will just replace L by J. So, J into J plus 1 h cross square by 2 mu r square. R square is r plus rho e, r square is Re plus rho, Re plus rho whole square, I am sorry, Re plus rho whole square. And this second term, the last term, will become half k rho square u of rho. This quantity can be written as 1 over Re plus rho whole square. I can write this as, if I take Re outside, Re square 1 plus rho by Re raised to the power of minus 2. Now, please see that rho Re represents the equilibrium distance, and Re represents the equilibrium distance, and rho represents the small vibrations around the equilibrium position. So, therefore, the quantity rho is much smaller than Re. For small vibrations, let me mention this once again, that I consider two atoms. This is the equilibrium position, Re. Now, this is now the atoms will vibrate about their equilibrium position, this atom and this atom also. But this distance, which I define as rho, because rho is equal to r minus Re, but rho itself is very small compared, if there are small vibrations, this distance is very small compared to Re. So, therefore, when I write 1 over r plus Re plus rho whole square, this is 1 over r square, this is 1 over r square. So, I take Re outside, and you will get 1 plus rho over Re raised to the power of minus 2. I can actually make a binomial expansion and I can still obtain the solutions, and one can show that the effect of this term is very small. So, as a first approximation, if rho is very small, I replace this by 1 over Re square, which is a constant. So, therefore, the term inside the square brackets was E minus j into j plus 1 h cross square by 2 mu r square. So, this will be approximately equal to E minus j into j plus 1 h cross square by 2 mu Re square. And then you have this term half k rho square minus half k rho square. So, this is just a constant now. This does not vary with rho. So, I represent this by E prime. So, the Schrodinger equation becomes, the radial part of the Schrodinger equation becomes d2u by d rho square plus 2 mu by h cross square E prime minus half k rho square u of rho is equal to 0. Now, if I compare this, if you recall, when we solved the one dimensional linear harmonic oscillator problem, then we had d2 psi by dx square plus 2 mu by h cross square E minus half k x square u psi of x is equal to 0. So, it is almost identical, it is identical, and therefore, we had obtained E, the energy eigenvalues of the problem, as n plus half h cross omega. Here we will write E prime, where n is equal to 0, 1, 2, 3, etc. Here E prime we will write, instead of n, the vibrational quantum number V plus half h cross omega. V plus half h cross omega, where V is known as the vibrational quantum number. And V takes the values 0, 1, 2, 3, 4, etc. So, if you recollect that the E prime which we had written down, E prime was equal to E minus j into j plus 1 h cross square by 2 mu Re square. So, this was equal to E minus j into j plus 1 h cross square by 2 mu Re square. So, the energy of the diatomic molecule will be represented as E as the rotational energy because of its angular momentum, 2 mu Re square, plus the vibrational energy. Here j is equal to 0, 1, 2, 3 and V is equal to 0, 1, 2. This is the vibrational quantum number V, and j is the rotational quantum number, and we call this, some books write this as E rotational energy and this as the vibrational energy, E R, E rot and E vibe. So, these are the very two, this is a very important expression that we have derived. The energy of a diatomic molecule consists of a rotational part and a vibrational part. Now, before we go further, I would like to mention one thing, that here in the when we solve the one dimensional linear harmonic oscillator problem, x was between plus infinity and minus infinity. You may remember that rho was equal to r minus r e. Rho is the spherical polar coordinate. So, r goes from 0 to infinity. So, let me write this down again. We have d2 u by d rho square plus 2 mu by h cross square e prime minus half k rho square, u of rho is equal to 0. So, rho is equal to r minus r e, and if you remember that the radial part of the wave function was given by r of r is equal to u of r by r. And so, therefore, for r of r to be finite at r equal to 0, so therefore, from this equation I can write down u of r is equal to r of r. So, therefore, at r equal to 0, this is 0. So, u of 0 is equal to 0. And of course, at infinity it is 0. So, r equal to 0 means rho equal to minus rho e. So, the boundary conditions are u at minus r e must be 0 and u at infinity must be 0. Now, and in the one dimensional case, as I mentioned, d2 psi by dx square plus in the one dimensional harmonic oscillator case, e minus half mu omega square x square psi of x is equal to 0. X goes from plus infinity to minus infinity. So, the psi at x is equal to minus infinity must be 0 and psi at x is equal to plus infinity must be 0. So, here u of plus infinity is 0, but u not at r equal to minus rho equal to minus infinity, but rho is equal to minus rho e. But since the values of rho for which the vibrations occur are much smaller than r e, this is approximately equivalent to u of minus infinity equal to 0. So, therefore, in this approximation, and which is really a very valid approximation, the energy spectrum, the energy levels corresponding to the diatomic molecule is given by this particular expression. This is an extremely important expression, and I would like all of you to remember this, and in my next lecture we will discuss the consequences of this equation, observe the vibrational rotational spectra of diatomic molecules like carbon monoxide, carbon oxide and carbon monoxide C and O, hydrogen chloride, hydrogen bromide and many other diatomic. The entire field of diatomic molecular spectroscopy can be understood by this particular equation. Of course, there are corrections to that, there we have made little approximations here and there, but otherwise more or less the rotational vibrational spectra of diatomic molecules. So, we have done really the fundamental problem in atomic physics, namely the hydrogen like atom problem, the fundamental problem in nuclear physics, the Deutron problem, and the fundamental problem in molecular spectra, namely the diatomic molecular problem. So, in our next lecture we will discuss the consequences of this equation. Thank you.